Hello, everyone. Thank you for joining us today for this first 2024 Rhino User Webinar. I am Guillermo Varela from Magni Europe, and I'm here today with Carlos Bausá from Zaha Hadid Architects. Carlos joined Zaha Hadid as the Sustainability Team Lead after almost 5 years at Foster & Partners, where he worked in the Specialist Modeling Group as an Environmental Design Analyst. His specialty in computational design and environmental simulation, combined with his expertise in sustainable architecture, allow him to propose and found the Zaha Hadid Architects In-house Sustainability Team to inform design decisions from the early stage. This webinar will focus on the new experimental design workflow developed by his team to create efficient envelope designs able to target the operational net zero status. Remember that in the last 15 minutes of this webinar, we will have some time for Q&A, so you can ask questions in the chat, and we will check them at the end. Also, I would like to mention that the webinar is being recorded and will be available on our YouTube channel, where you can find more webinars and tutorials. I want to thank Carlos for accepting our invitation, and that's all from my side. So you can start with the presentation if you are ready, Carlos.
Okay, thank you, Guillermo. Thank you for the introduction. I'm going to share my screen now so you guys can see what we have here. I think, can you see now the presentation? I think it's being run in a second. Fantastic. Okay.
Yeah, great.
Well, thank you, Guillermo, and thank you, Magni, for the invitation. I think it's a great pleasure to be here with you guys, so I can share a little bit of the work that my team, the sustainability team, has been developing over the last 3.5 years, 4 years almost. As you said, just to introduce myself a little bit, I'm Carlos Bausá, the head of sustainability of Zaha Hadid Architects. I'm senior associate. And just to give you a background on who I am and why I'm presenting this thing here, I'm an architect, so that's basically my background. I studied in Barcelona, actually, in IAAC. I did my master in advanced architecture there. And all the time I became lead AP and a qualified energy assessor. I've been working in between Zaha and Foster's for in total 9 years, doing a lot of work in between environmental analysis, sustainability certification. But because I have a background in architectural, computational design and visualization, I had the chance to start kind of merging both worlds, the work of environmental engineering and sustainability and the work of design, the world of design. And with these ideas, I came to Zaha, and I had the opportunity to join Zaha to found the sustainability team, which I will introduce you right now. So sustainability team we're kind of a very small team, let's say. We are 6 people in total. Between us, we have all of us, we are lead APs and or lead green associates. Everybody in the team has background in architecture, but everybody's trained also on computational design. So we work a lot on trying to merge the way design works with all the targets that we need to achieve and fulfill in the sustainability area. So for us, it's very important that the design that we're doing in this company, in Zaha Hadid, has a background in sustainability. And given the complexity of the geometries that our teams are developing here, we need to develop very specific workflows to inform the design decisions, especially on the early stages. So my team and I have been working in around 100 competitions in 4.5 years since we started here the first time. So we work on providing feedback to all of the architectural teams, especially when they are working on competitions on early stages. But also we work on early stages and later stages that are more technical, so we can create a unified approach to sustainability in every single project. So we are kind of an in-house consultancy, let's say, that serves everybody in the company, or try to serve as much as possible all the projects. We work a lot with external consultants as well. Obviously, as you can understand, 5 people is not working with every single thing, every single aspect, but we try to coordinate with them what could be the best approach and work on the engineering aspects later on, so we can have all the projects deliver with the same level of depth and quality in their sustainability. Just for you to introduce you, this presentation is going to have 3 parts. So let's say the first one is going to be an introduction of the environmental analysis workflows, sort of like a summary, so you can understand a bit better how we need to target sustainability connected to environmental analysis and computational design. This is going to be the first one. Then later, I will focus a little bit more on the topic of this lecture that is mostly, reducing embodied carbon and operational carbon so we can create net zero buildings. I will go through an explanation of the steps that we normally follow to create, to optimize geometries so we can reduce especially operational carbon. And also like an introduction on how we operate with tools that can help us to achieve understanding of the whole life carbon, basically on the embodied carbon side of the building. So to start with this, I mean, obviously, the reason why we started to talk about sustainability first, and create a team in-house to develop, all the studies that we're doing is because we are concerned about the CO2 footprint of the buildings, because buildings itself, according to the United Nations Global Status Report, is responsible of 37% of the global CO2 emissions. So that's massive. That means that as architects and builders, we have somehow a responsibility on the way we design so we can reduce emissions. A lot of it, you will see later, it's really connected to the operational emissions, to the operational, area of the building. And another big part is also connected to embodied. But because of the design decisions that we do in the buildings, we are responsible of this footprint. We work a lot on trying to minimize it as much as possible, and work with the clients, work with the consultants and with the project teams, so they can understand what are the main targets that we need to fulfill in order to reduce this. I mean, something that probably most of you know is that in 2030 there are like certain goals that need to be met towards becoming carbon neutral, and they have been proposed by the Paris Agreement and by different regulations set up by the countries who kind of joined the Paris Agreement, or even by the sustainability certifications, which are kind of like connected to this in a way. So, but the problem is that the reductions that we need to target is like 45% by 2030 of the global emissions if we want to, reduce global warming or keep global warming not higher than 1.5 degrees. But the problem is that the reality is totally different. So we can see that there is actually like a projected 10% of increase of global emissions if we continue working the way we are working right now. So we think that as designers and architects, everybody has, its part. Everybody can just work a little bit in order to help on these reductions. So we then go and continue delivering things if we continue working with this business as usual approach. I mean, something that's easy to understand is like whatever you do in one country, if you pollute in one side, it's going to be affecting other places in the world. This is because we are connected by the atmosphere and everything travels. So for us, an architectural company like us, which is such an international practice, we need to think about, solutions that can work for different climates and for different countries. So each building will have, something different if it's created in a different location. So in order to target sustainability, we look at especially the structure of different sustainability certifications. I'm not going to go in each one of these categories. You will see that this presentation is going to be more focused on energy and carbon. But things like the way we deal with water resources or even transportation and the materials that we have in the buildings will have an impact on the certification. So we'll get higher or lower levels in the certification process. But at the same time, what matters is like climate change. So everything that we do is having climate change in the back of our minds. We're trying to make buildings that are going to somehow help to mitigate global warming. And this is possible if we reduce the carbon footprint of the buildings. Zaha Hadid, since 2010, has been systematically certifying every single project that we built. We are quite proud that we have been achieving like very high levels of sustainability standards since that date until today. And so I'm hoping that the future generations of buildings will be even better. But yeah, we have been working a lot on certifying our buildings to basically show that buildings can still be very sustainable, even with the complex geometries that we are delivering. How we start this process is by engaging very early on the design process. So instead of leaving it for, when everything has been agreed, our team and our consultants, the one that we're working with, we made them engage very early with the design team and the client so that they can understand what are the requirements for each different country. So it's like we do lots of research about, what are the targets that the country will have, or what are the targets based on the requirements of the client. And we need to, with this information, we brief our project architects. And with that, we can help them to take informed decisions at very early stages, which will lead to much better sustainability scores or let's say net zero targets to be met in the future once these buildings are, already on site. Obviously, there are like associated costs. We all know it, but we know that there's a return on investment that normally is possible to retrieve this by just only savings in energy. After 5 to 6 years, there's lots of research that probably you must be aware of it that would tell you that the return on investment normally is around it takes around 5 to 6 years. But when you do like green buildings and you add new technologies to make buildings more efficient, you increase the property values, you increase the lifespan of the building. You even have access to public funds. Some countries can help the clients to achieve, like this green building status by giving them money, which is something that you cannot do if you have a normal building or a building that is not meeting this sort of requirements. And it will have an impact on the users, which is, we are doing this as a human-centric approach. We think about the people first, and we think how the people is going to feel inside of the buildings. And we try to focus on that on a daily basis, so all the projects gets focus on improving the lifestyle or the life quality and productivity of those people working inside and living inside. In order to target that and achieve this, we have a workflow that what it does, it somehow try to inform how to make more passive design. So we work on making lots of assessment to benchmark different building iterations. As you know, when you're working in an architectural company, you do lots of versions of one building. But in order to find the best option, it's not only the aesthetics that matter. There's a big process of benchmarking with real data and numbers, so we can understand if one iteration is going to improve, the passive behavior, and it's going to have, reduced energy demand, or if it's going to have higher levels of sustainability embedded. Just only on early stages, we can do a checklist to understand if this things will be happening in 1 building or not. So this way, the teams can be informed very early and adapt their strategies to help them to accommodate a more sustainable building. We do simulation, and with the simulation, we do optimization. So based on the data, we can optimize each iteration. And at the same time, we target reducing carbon. This is something that you will see that we use like lots of different simulation tools, especially solar help us a lot. Solar analysis with Ladybug in Grasshopper help us a lot. We have developed our own custom algorithms based on a few tools that you will see later to be able to understand, solar access, how the buildings are going to work. And see if the studies also, they help us a lot to understand comfort outdoors and indoors as well, which will have an impact on reducing the need of mechanical ventilation. If we are using CFD, we can understand prevailing winds, how they are going to actually impact the buildings. So, and I guess I'm going to give you a quick intro of how we operate with each one of these ones that I just, each one of these workflows that I just described. First is the solar exposure. That's the one that we use at the very beginning. After understanding the climate, we do climate analysis and develop reports, which are quite deep on understanding, all the comfort levels that they're going to have. And the requirements that each climate is going to have, because it's not the same building something in, let's say, a place like Barcelona or London than building something in Dubai or building something in a northern area, which is, that could be quite cold. So we look at reducing as much as possible solar heat gains if we're working with in climates that can be hot and humid, especially. So we develop geometries that can be working with the solar angles, and that's something that is possible thanks to data tools, which we have been using a lot just to calculate solar dynamics. And they help us a lot to define things like angles for shading or different solutions to mitigate the sun on the buildings that we are creating. At the same time, we use these tools for mitigating, for example, solar exposure on the exteriors. If we're doing a master plan, we like to think that we are in a warm climate like the ones from Saudi Arabia or Dubai, where we have like lots of projects. You can understand that it's going to be different than having a building in Europe. So we need to try to explain to teams where we are going to need shading systems or shading devices to make the outdoor spaces more comfortable. So with this information and this sort of maps, that's kind of like a heat map, we can inform the clients and inform the project leaders where do they need to act. Because some areas probably won't need that much, but if we are like creating public spaces that are meant to be usable by everybody and enjoyable, we need to protect them from the conditions. In the same way, if we have a project in a northern location where light daylight could be lacking for the latitude that we're working on, we try to maximize the amount of solar access for everybody to enjoy the right comfort levels there. So we work a lot with this sort of analysis and algorithms to create catalogs of solutions. So based on the analysis have a direct repercussion on the location of these solutions that we're going to work with. Shading, for example, is something that we can design with very different aesthetics, but the location normally is driven by this sort of studies. So this way we can work only in the places where we know this is necessary and this could be a requirement, and then leave other areas without this protection in case that they don't need them. So it's very surgical, and that helps us to reduce the amount of materials or elements that we're going to need, therefore reducing the budget. At the same time, connected to solar, we do glare studies. That's something that helps us to mitigate, for example, the issues that could be connected to reflections of light or glare, potential glare that can happen if we are making a building that has high level of glazing or in the surfaces of the facade. At the same time, if we're using a building that has a reflective surface for different materials, we can forecast where we're going to have glare, or in this case, like in this image, where we can have something that we call solar convergence, that is concentration of sunlight due to curved facades. And thanks to that, we can inform and develop solutions so we can deliver the shape that we want, but without the associated problems that these shapes could have in terms of reflections. For example, this analysis that you're seeing is just an animation hour by hour of the reflections of the sun in one location based on the reflectivity of the facade. So we can understand very precisely where we can have a hotspot and which areas of the facade could be responsible for this issue. Once we know this, we do maps, we do like back tracing studies, so we can see how much radiation is coming from one segment of the facade. And then we can mitigate the issues by adding additional geometries that can help us to have the shape that our designers wanted to transmit, or the shape that the client was interested in, without any associated problem that could bother the people around the areas. So in this case, for example, for Opel is a good example, because this is one of the first projects where we did this science-driven design process, because we use a scientific method to assess the reflections and target only a treatment area on the facade that is quite optimized. So we don't need to use excessive material. So the solution here, after testing different things, we decided to go ahead with this sort of louver system. You can see here like a mock-up of this. The building is under construction now, so hopefully will be soon built. But in this case, we work closely with engineers that help us to validate all the studies that we were doing here in-house for this topic. Connected to wind simulations, we have a specialist in our team which work closely with this CFD simulation software, and that helps us a lot to make wind maps and comfort maps of the exteriors. So we can forecast, even before something gets built, which areas will be more likely to have strong winds because of different geometry sizes or facades that can be capturing wind, or even like small alleyways or narrow streets, which can be channeling the wind because of the Venturi effect. We know exactly where this can happen before getting built, because we can work with the local prevalent winds that we know from weather files. They give us the information, and we can inform the architects so they can take decisions on moving, for example, entrances to locations that are going to be more calm, or even add geometries that can help us to reduce the downdraft wind, for example, or this sort of wind channeling effect. With this work that we do, we kind of like produce studies that later can help us to do things like, for example, here in this project that we did in Rabat, we understood which locations will be affected by strong winds and move the accesses to be on the locations where we are going to have less strong winds. That's something that every architect work with us, so we can deliver this systematically to a single project. Indoor natural ventilation is something that we also work with, and we do analysis so we can improve the interior distribution, so we can ensure natural ventilation is going to happen. This way we can reduce the need of mechanical ventilation, and even ducts, which will have an impact on the embodied carbon later, as you will see. And we just try every simulation, and we deliver the same information in different formats so everybody can understand this in 2D, 3D, and get an understanding of how comfort will happen. For example, this is one of the projects that is also under construction right now, Xianxinge Cultural Center in China. And here we did also a similar study for allocating outdoor landscape features where people was meant to be resting. So we were allocating landscape in the places where we know there will be less wind. Interior daylight, that's another important topic that we work a lot with. We basically we have a very interesting workflow to calculate natural distribution of light. And we can calculate things like spatial daylight autonomy or our solar exposure to see if we are going to meet the targets from, for example, like the LEED or BREEAM are proposing, and see beforehand if the building will meet it. And if it doesn't, we just work out with our design team solutions so we can improve things like daylight distribution to reduce the dependency of artificial light. So this is an analysis that at the beginning, so when you're doing a building, it's hard to understand if you're going to have enough light in one space. Normally, it's hard to forecast nothing without this sort of analysis. But with that, we can precisely know which areas are going to meet and the percentage of area that's going to meet the requirements for natural light. Then later, what we do, we just go on site. For example, for Infinitus, we did the analysis and later went on site to double check. And we were like quite relieved to see that the values of what we're getting were meeting the expectations. So a lot of studies happen on site later with our local engineers who give us the values, and we can understand with these post-occupancy studies if the analysis has been done correctly. If not, we just work on tweaking so the next generation will be more efficient. But normally we're happy that the workflow that we have right now is quite robust and it never failed. We work this with all projects. We do it systematically in every competition. That's a really important workflow because this helped us a lot to think about the way we are dealing with interiors. And even before submitting the competitions, we try to make every single space work for meeting the requirements. Materials, it's a very important topic, and because this is really connected to the embodied carbon. So we work with all the stages of embodied carbon, and we do the whole life cycle assessment. And that basically considers the operational carbon and the embodied carbon over the whole life of the building. So we look at all the stages from extraction of materials to delivery of assemblies on site, construction, and end of cycle. So towards creating a more circular approach, either at, let's say, architectural level and also at urban scale level. Thanks to the studies that we develop with embodied carbon, we have lots of databases that can give us this information about each one of the materials that we are going to work with. A lot of the projects that we have been delivering have very good basis on this topic, and they have been delivered with highly efficient building materials with low carbon footprint. Being timber, one of the main ones that we work with. Unfortunately, not all the countries are allowed to work with timber, which is sometimes in China it's not easy to propose timber structures because of the regulation and the fire regulations that they have there. But the ones that we have the chance to propose materials, if we see that the client's interested on it, we work on that. At the same time, we also work with what is called green concrete solutions, which have lower carbon footprint thanks to different processes and materials which are aggregated into the mix. The studies that we develop, what we do is informing even the material decision and the material selection with LCA tools. So we can now the materials available in one location, thanks to the research that our team does with the local architects and the local engineers. And with the information that we get from them, we make these studies. So before even a team has decided what materials are going to choose, we just give them a selection of the ones that could have lower carbon footprint, so they can inform their decisions based on this and try to select the ones that are going to have, a lower carbon footprint. Therefore, we work a lot on circularity as well. So we think that every project all the materials should be reused or recycled as much as possible. So a lot of the research that we propose internally with our team to the architectural teams is about circularity, on solutions and strategies that they can use for having a circular approach at even architectural level or urban scale level. Obviously, when we see that it's not possible to reduce more the carbon through the mitigation solutions that we propose, we also propose options for offsetting carbon to the clients that could be responsible and that can be efficient. So there's a whole chapter about it that we normally discuss with every single project or project leader. And you will see later some of the numbers that we run, so you can understand the process that we follow in that topic. When it comes to energy, that's one of the, let's say, most important additions to our team, is to consider the energy flow since the very beginning. So we have a new workflow that we started to develop a year ago, to basically help people understand that, and project leaders and also clients, that the cities and the buildings that we are developing can be energy producers. Therefore, if we have this in mind, we are going to be able to deliver a more, say, climate conscious proposal. Because if we are able to make buildings to produce their own energy or produce as much as possible renewable energy, we'll be able to detach from the grids and reduce the sizes of the grids. Right now, the grids, sometimes you will see that some cities, they need to basically cut their electricity at certain moments when the demand is high. And that's mainly because everything is controlled by one central. So when they don't have enough energy, they need to basically reduce the amount of energy that they deliver. But if you make buildings produce their own energy, or at least produce a percentage of the energy demand they have from their own renewable systems, it's something that's going to help the grids to be smaller and therefore have less pollution and less contribution to global CO2 emissions. So as much as possible, we try to always deliver these ideas to our clients, hoping that they will accept it. I mean, not all the projects or all the clients have exactly the same approach to design or to making the projects that they are asking for, but we have seen a change, and we have seen lots of people really concerned about having energy demands in high levels, and they basically allow us to propose these things, which is quite remarkable and useful in order to transition to a more cleaner energy system in the future. But in order to, before that, we do a lot of work on producing buildings that are going to have what we call energy efficiency measurements. The acronym that you will see that I use over this over the next half of this presentation is EM, just to simplify things a little bit. And the energy efficiency measurements are solutions that, through passive design or material assemblies or facade developments that we're going to deliver, we're going to be able to reduce the energy demand. Because at the end, energy in the building is mostly connected to creating the conditions of comfort inside of the building, so people can work and stay inside without feeling, let's say, too hot or too cold because of the climate outside. So the building envelopes will play a crucial role into reducing the energy demand, which will have an impact on the embodied carbon and operational and embodied carbon at the end, as you will see. Some of them are connected to increasing the amount of daylight, or using efficient equipment, or using systems for controlling solar heat gains. And at the same time, all these things together with renewables will help us to reduce and create an energy efficient building. We use energy modeling, and I will give a kind of brief overview of how we use Honeybee, Energy Plus, and Open Studio to get basically these 6 results. So basically, we look at comfort, at creating microclimatic maps, and study the chances of overheating in a building. At the same time, we study what's going to be the thermal usage of the building and the energy balance based on all the services and systems we're going to have in the building. That help us to create better, let's say, conditions for the buildings to work. And thanks to the energy performance in early stages, we can reduce the energy demand, as you will see later. Once we have done this, we normally do these breakdowns of to understand how each one of the systems that we are going to have inside the building are going to consume energy. So we know exactly how much energy lighting will consume, or things like cooling and heating, how they're going to be, improved by the passive system that we are going to use in the building. So said that, I'm going to start with Chrysalis. That this is like one of our research and development projects. For obvious reasons, I cannot show confidential projects, so I'm gonna just kind of give you a breakdown of the steps that we follow with this internal research project that we developed to basically showcase to our clients and teams how this workflow works in order to make more energy efficient buildings. So we developed one, let's say, ideal building in Barcelona. It was not done on purpose, but when we start thinking of this research project, I think because, obviously this kind of like thinking, let's see, which city do we choose for making a building? We thought like about Barcelona because it has a very hot climate these days, especially because of global warming. So we thought like if we have to develop like a building that is, as much as possible, carbon neutral or passive, let's think about a climates that can be suitable for that. So we thought about using the weatherfly from Barcelona that you will see later. But the first thing that we do when we want to make projects, that we develop a tool basically to interrogate how easy it will be to have a net zero building in a specific location. So we call it climate discovery tool, and that's something that our team developed by creating like a mass data analysis of every single weather file around the world. So we can know before even getting built something, how much is going to be a rough estimate of the energy consumption the building will have based on the climate. And at the same time, we can understand which are going to be the comfort levels based on something called UTCI, that is the Universal Thermal Climate Index. That is like kind of like the perception that you have of the weather in one location and the comfort that you're going to have. So we can know before even building something, what are the chances of comfort in one location. So what could be the percentage of comfort over the whole year. So we can precisely calculate if the building will need air conditioning for how long this air conditioner will be working or for how long the heating will be working. Once we know that, we also need to understand that this is going to have an impact on the energy demand. So with this tool, we calculate like baseline buildings. So we introduce the GFA of the building, and we can know beforehand what could be the baseline consumption for the specific location. And at the same time, we can understand how much energy from solar, for example, we are going to need to make the building net zero. So let's say we can classify the whole planet and color code each city based on a ranking that we give to these points, to these locations. And we can know how easy it would be to be net zero there. Obviously, we use this tool as a strategic tool for taking decisions on where do we want to build things if we have the chance to do it. But if a project comes to us and they tell us, we are building something here, can you tell me what's the potential? We can do it with this tool. So it became quite strategic and quite useful for our teams to work with this. And that's something that we have internally here at ZHA. So then later, once we know what the potential is, we can, for Chrysalis in this case, we start working with sub-D modeling. So we start making lots of work on creating an aesthetic that could be similar to the path that we follow here for making buildings. But in this case, we work with sub-D from Rhino. So sub-D helped us a lot to create very similar like looking geometries than the ones that we create in Autodesk Maya here in the office. And so my team started to work on having this approach of modeling something with sub-D, and then later extract the surfaces so we can create a computational design on top of these surfaces on sub-D to create a parametric shading system. Because we are working on a warm climate for this specific project, we have to develop a shading system, sort of like a secondary skin, that could help to protect the southwest and southeast facades. As you can see, the shape is not arbitrary. We try to reduce the south facade, which is the one that's having high level of exposure, and to reduce a little bit the directionality towards the east and west and of the facades to reduce the amount of solar heat gains. So at the same time, we reduce the footprint so we can give more space to the public space and add more greenery around the premises without losing GFA by increasing the height of the tower. So we did a very nice method to compute that with basically grasshopper. But on top of that, normally every time we start a project, we start looking at what are the elements that we need to have on the building to make it work, as passive as possible, To reduce the energy consumption, we did this diagram to basically explain ourselves what could be the systems that we can integrate to add cross ventilation, to introduce as much as possible renewable energies, or capture rainwater and store it under the building, so we can have reservoir of water without needing too much water from the grid, and creating the shading system to reduce the amount of solar heat gains. So this is the way we start projects in Zaha. Normally we work with these sort of diagrams every time there is like a project arriving to us. So we did the same for this process. We start thinking what could be what we need to add. I also start thinking on the orientation. So if we look at the sun path, you will see that the south facade or the southwest and southeast facades are looking towards the areas that have the biggest amount of solar exposure. But because it's impossible to make a building that has facades looking south or southwest, we need to add shading to it, especially if we're in a warm climate. This way you can see that the north facade is the one that has a little bit more level of glazing. But overall, the glazing level for this, the walls, what we call window to wall ratio, is around 50%, which is kind of low compared to other full glazed buildings for offices. Yeah, I think I forgot to mention that this is meant to be an office building, commercial building. So as you can see on the left of this image, I think I didn't show it earlier, we have like something that looks like a benchmark, like a scoring. So we have a scoring system that we develop internally to basically give points based on the passive design features that the buildings are having. So it's something that is not like an official certification system, but we develop it internally here in Zaha to give an understanding to the project architects of how is it or how passive the building could behave. So therefore, later when we know that as soon as we do calculations for energy, we're going to start seeing reductions on this graphic that you can see there, that the energy loads will start going down in every single iteration of the building, or after we add a new feature. For example, if by doing the orientation and by doing the shading, we can see that there's a reduction of 5.9% of the energy demand because it's reducing the solar heat gains. At the same time, here we can see reductions on the amount of glass, which adds a little bit more reduction to the overall baseline energy consumption that the building is going to have. Then we continue adding things and we continue optimizing the shading. So at the beginning, we started with a vertical shading element, then later we start inclining it, and you will see that we have also like an algorithm for optimization. We use Galapagos in this case, and Wallace as well, we have been using it. But with this, we can basically give the algorithm the freedom of defining what could be the best inclination for a shading element. So this algorithm, what it does is kind of like creating like lots of movements around of the inclination of this element until we get the right angle. So that's something that helps us a lot to inform the way we are kind of creating a shading system for a facade. Because very often people oversimplify shadings. They make them with one orientation without thinking, what's the orientation of the facade, and if this inclination is going to be good for that orientation of the facade. So once we know that, we can also move forward and think about the natural ventilation systems. So in this case, we try to reduce the amount of services for ventilation by adding natural ventilation inlets. And we calculate what's going to be the wind speed and the comfort levels inside of the building, so we can allocate also the distribution of the working spaces, in this case for an office building. That's something that we work in every single project. And we deliver these results in many different ways. As I showed you earlier, we can work with 2D maps. We can also work with 3D wind strokes that give us a better understanding of how the air is going to move inside of the building. And the colors are based on wind speed. So we can understand, the chances for the wind to move inside of the building without, creating discomfort around. You can see that by adding natural ventilation, together with everything else that you showed earlier, we are already at 10% reduction of the energy demands. Then as soon as we start kind of thinking on natural light, when we add to our energy modeling natural light contribution, then you can even lower more the energy. So little by little, we are reducing. What you can see here is that little by little, we are reducing the amount of energy that the building is going to consume. It's very important because every little counts towards making a net zero building, especially when you are on the operational side. So when we do the distribution of lights, we try to maximize, the amount of daylight access by having, different materials on the facades, which won't, remove light, especially light colors will help to get diffuse light inside the buildings. And the distribution of the seating layout is connected to the daylight. That's something that we do very often in every single project that we work here in Zaha. Now, I'm going to give you a little bit of kind of like a explanation of how we do the energy modeling. You will see also some sober stuff here soon. But when we do energy modeling, that's something that we do at very early stages before we go very deep into the design or technical stages. The energy modeling helps us to understand how the buildings are gonna operate. So we need to really create this study to inform the design decisions and see if we can, improve something. I mean, if your approach is robust enough, maybe you don't need to work a lot on improvements. But if you don't do it, it's very hard that without the energy modeling, you're going to know if your building is going to be energy efficient or not. Because we need to target the net zero building, and the new generations of buildings should be net zero. This is the way to go. And actually, if you look at LEED or BREEAM, they will recommend you to do the energy modeling on a very simplified geometry at early stages, so you can inform your teams on what could be the best way to proceed. So when we look at doing energy modeling and this simulation, we need to consider everything. We need to consider the floor plans and the geometry. So you will need to do even a simplification of the geometry for the tools that we'll show you later. And we need to calculate how HVAC systems, lightings, and everything is going to have an impact on the energy demand. So you need to consider every single thing that at this stage you have, because obviously at every stage you don't have everything, but you can make assumptions on, if you're following the codes of one location, these codes will give you the assumptions that you need to do on early stages. Once you want to go into the actual analysis, you cannot throw the geometry as you have it in the renderers. So if I go with this geometry instead of a rendering, energy modeling engine, it will never work. So maybe the people who's listening now who is not used to energy modeling, maybe they don't know. It's something that we have to do here a lot, is working with the architects. And if they are not aware of the process that it takes to simplify the geometry for energy modeling, it's a big problem. So for us, it took us some time to make architects understand of the time that it takes to simplify the geometry and prepare it. So the energy modeling engines can accept it and do their numbers based on that. So normally what you need to do is create a very basic envelope that contains the same gross floor area and window to wall ratio. As much as possible, it needs to be very close to what you have in reality or what you're going to build in reality. You need to also add the shading systems in a very simplified manner. Normally it's like a surface, very minimal, because if you add like volumetric elements, it's going to crash. So it will take forever to compute. So you have to be mindful of the resources of the type of computer that you're working with. Obviously, if you have a very big computer, you can throw more complexity at it. But even if you have an amazing computer, the bottleneck and is the engine itself, which doesn't allow you to have things with all the geometry, with all the curves or everything. So normally a curve geometry, we need to simplify it a lot, make it faceted or very polygonal. But at the same time, we have developed a workflow that gives us a very accurate model at the end of the day, instead of having a stack of boxes one on top of each other. So we can add more accuracy to the energy modeling at the end of the day. This is a process that can take around 2 to 4 days for a skillful 3D designer. So our team normally does it in between 2 to 3 to 4 days for a tower like the one that you're seeing here in this model. If it's a bigger model with more complexity, obviously it requires like more time. But that's, let's say, that's the average of what I've seen around. So just for you to understand a little bit better that thing in 3D, this is how the building looks like when we start modeling it, after we have baked all the geometries from grasshopper and everything. And as soon as you want to go into the energy modeling, this is how it looks like. Everything has to be simplified a lot. So you will see that even if it looks like really not the same building, still preserves the same amount of area of glass and the same proportion of openings. Once you have done this, you also need to define zones. And the zones basically are the rooms which are going to have the same HVAC or lighting systems. And once you have everything, you can throw it inside of the script. This is like the script that we have developed for energy simulation, which is kind of simplified here, but it considers the materials that you have applied, the geometries, the HVAC simulations, and everything needs to be plugged into the energy modeling, which is basically almost the last column. We compare baseline building with the optimized building, and we see with these graphics, the information that we get is the percentage of reduction of energy. So it's quite accurate. Now we can understand from the scratch how each one of these energy efficiency measurements, how are they going to contribute to reduce the energy demand. So in this case, for example, for Chrysalis, we got like on heating and cooling only, we got like a 46% with all the energy reductions, the energy efficiency measurements that we applied. And here is before even having renewables. So that means that if you do the right work on the design aspects, you can have an amazingly energy efficient building without even renewables, which for that you will get lots of points in LEED. Overall, for this tower, the comparative with the baseline building using the ASRE, let's say, all the ASRE features. ASRE is even defining the type of material assemblies that you're going to have, and the properties for these assemblies for walls, facade, glazing, etc. If you propose improvements, obviously that's the point of view of doing these studies, is that you need to propose these improvements and compare it with the ASRE baseline model. With that, you can get an understanding of how improved your building is going to be. That's normally the standard method or procedure to do energy modeling nowadays. In this case, for this project, we got like a total reduction of 26% reduction of energy demand of the annual demand of energy that we're going to have for the whole services altogether working in the building. And what you can see here, this something funny that we did is just to show you that the breakdown of each one of the scenarios where we are applying, in each column, we apply one measurement. And you can see that for each one of these measurements, we start reducing the amount of energy demand compared to the baseline column that's on the left. So once we reach to the case number 5 column, that's the one where we have the 26% reduction, which is kind of good. And we are happy with that at this stage. But then the magic happens as soon as you apply renewables into the facades or in the premises of the building, where you can reduce to 0 the amount of energy demands that you're going to have there. I mean, there's not a single building that doesn't consume energy, even with passive design, even doing like the most amazing building in the world, with a smaller footprint in the world, all of the buildings will have certain consumption of energy, because at a certain point you will need to even, switch on one light. But what this process means is that you can target reductions through this efficiencies, through this system of adding energy efficiency measurements. And if you include renewables at the end, that's when you're going to be able to reduce to 0 your dependency of fossil fuels, because all the energy can come from your own renewables. So another step, that's the step of renewables, is like we can calculate how much energy is going to arrive to the shading devices that we have in this case for this building. So we calculated the amount of the area of these shading devices that would be suitable for having solar panels. Obviously, because there's overshadowing in a shading device, you need to compute which area could be suitable for that. I mean, depending on your type of geometry or type of building, you can even have solar panels directly on a cladding system that is opaque. And there are like lots of elements in the market that you can use. Like there's like PV panels for facades. There are PV panels for glazing that they can be integrated in the glazing. You don't even see it because they look like tinted glass. So we work on delivering this sort of information to every single project and calculate which is the amount of area that can contribute to solar panels. So, but obviously, if you are able to contribute with the facade solar panels to, let's say, 20% of the energy demand, still you need to find a way to reduce the rest of the energy by having solar panels somewhere else. This is called still an offset. This is an offset practice. But if you are the owner of the solar panels and they work for your building, that's a totally legal practice, and it's really useful for mitigating the amount of energy demand that you're going to have. So we calculated that for a building like this, the amount of solar panels that you need is equivalent to 1 football fields and a half almost. So it's not that much if you think that you can make a building in a master plan and you can allocate this on the master plan, or you can have solar panels or the landscape area. or even you can have the solar panels on a nearby piece of land to serve your building, if you have the chance. Obviously, if you are in the middle of a city, that's harder, but you still can have the chance to get the solar panels somewhere else, or even buy what we call renewable energy certificates, which is like an energy provider that gives you electricity from renewables. This way, that's a practice that even leads will consider as valid, and they will give you points for that, and they will consider your building net zero, operational net zero at this stage. But then the other question in the air is like, what happened to the embodied carbon? The one that is connected to materials, the one that's connected to the construction process, etc. So we developed another workflow to calculate embodied carbon, thanks to a tool that we use nowadays that is called One-Click LCA. And One-Click LCA helps us to get an understanding of the amount of energy that the building will be consuming, or so the amount of emissions that the building will be responsible for over the life cycle. So in this building, we were even below the EU 2030 targets, which is we're quite happy, because at this stage, obviously, it's very early to be 100% precise. But with this studies that we've done at this stage, we can be 80 or even 85% precise on the embodied carbon footprint. Obviously, to be 100% precise, you need to have your building in a BIM model, totally finished, with every single nut and bolt already in the 3D model, so you can calculate that. But at early stages, this is still very useful, because that can give you an impression if you're going into the right track or not. So we collect the data from the project brief. Also, we have to develop a model, which is very specific for LCA. Is you cannot throw the building the way it is, or the geometry straightforward from Maya, from Subdit. You need to add some treatment to the geometries and classify everything. You will see later. And once we have classified everything and transformed the geometry, I mean, here in this case, it'll be more easy than the energy modeling processing. But here we have a workflow. There is a workflow in between Rhino modeling and Grasshopper modeling, so we can transform the geometries in something that One-Click LCA will be able to work with. So we have even an algorithm in Grasshopper that push all the information into One-Click LCA and give us all what we need to do the lifecycle assessment. But overall, just for you to have an idea, for those who know how to work with embodied or lifecycle assessments, you are quite familiar with the process of classifying the geometries. So you need to understand and separate everything by material, obviously. And here, in this case, we separated the structure from the cores, from the glazing systems, from the shading, from the partition, etc., to create a model that will be able to be inserted in One-Click LCA. So here you can see that you also have to be very careful on the way that you classified your geometries in Rhino, because that will simplify the process of exporting materials to the One-Click LCA platform. So we have to do a lot of work on classifying every single material with the right structure. So once we input everything in One-Click LCA, so in Grasshopper, we can assign the right material and the right properties to them based on the informations from the environmental product declarations, which are like documents that every manufacturer releases, where you can find information about the, let's say, global warming potential that each one of these materials are going to have. Once you have everything in Grasshopper, we can push it inside of One-Click LCA, and it gets perfectly sorted. And we can know exactly the volumes and square meters of each one of these materials, run the lifecycle assessment, and get graphics that later we can use to interrogate, the building itself, and understand which areas will need to be, treated, or which solution we can add to reduce the amount of embodied carbon from each one of these things. So as you can see here, this is a breakdown of each one of the results, or of each one of the areas, the contribution to the overall embodied carbon footprints that the building is going to have. So systems, for example, and structure has the biggest contribution. So what we take from here is like the more passive your building is, and the more reduces the needs. So if you must reduce the amount of ducts that you're going to have on a building, or the need of centralized HVAC systems, you will be able to reduce the carbon footprint. So if at certain stage you know that you're not going to need them, you need to introduce that thing in the tool, so we can even make a more efficient calculation and more accurate. But again, that happens later in later stages. At the beginning, the tool will make its assumptions, so we play with the information that we get from the geometry that we provided. And once you have done this and you have calculated the operational energy and the embodied carbon, you throw everything here, and when you get the whole life cycle, the whole life carbon of the building, that's when you can see, the amount of contribution that operational carbon has. It's massive. So over the life cycle of a building, the amount of energy that you're going to consume because of heating and cooling and services and lighting and everything is going to be 3 times bigger than the normal embodied carbon, even more. It very much depends how your building looks like. If you have done a building where you have done a lot of passive design, you will see that the contribution is lower. And then the embodied carbon contribution will look bigger. Still, even the numbers can remain the same. But this tells us that every time someone asks me, where should we focus first, Carlos? What do we do here? Well, do we need to create like a totally net zero building from looking at the embodied carbon only? Or should I look at making a more energy efficient envelope? So my first suggestion is you need to look at the climate and make a very energy efficient envelope so we can reduce the operational carbon. Because if we do that thing, this is a breakdown that's very interesting. So we came across with this graphic a few days ago. It's let's put this together so we can show to the people that if you have a base case compared to a building that has energy efficient measurements, the reduction can be massive. But as soon as you add, PV panels on the facade, it's even more. So what we need to do is try to get rid of the operational side by adding as much as possible renewable energy. So we can have a building that's going to be totally net zero in that sense. So we just need to think about offsetting the embodied carbon, which is normally, inherent to the way of construction. And you cannot get rid of that, but you can get rid of operational energy by just adding solar panels to the building. And that's the first step of making a net zero building. Let's balance the operational energy to zero with renewable energies. If we manage to do it, then we have covered the biggest problem of the building. Then later, we need to think, what do we do with the extra, embodied carbon that is connected to the materials and the construction, and even the decommission of the building once the building is, the life cycle has passed. So you can see here that the addition of renewables can reduce around 10%. If you just only with the facade that we have in this project, we must reduce it to 10%. But as soon as you add the additional renewables that can be connected to the building somewhere, but still detached from the building, that's how we get the net zero operational building. And then through research papers, we wanted to do something that we do very often, is giving to the teams an idea of how much forest would you need to reduce the amount of carbon of your building, the amount of embodied carbon. So for Chrysalis, we found interesting research papers around that can give us information about how to do these calculations. I feel you guys will find this information as well. Everything is available on the internet. But it's important to do these numbers because that gives you a dimension of how much forest land you need to preserve over the life cycle of this building to be able to reduce the embodied carbon of your building to zero. Obviously, we are kind of presenting this and suggesting this very often because that's kind of like a mainstream offsetting strategy that we have seen in many, many different projects. Obviously, there are different projects of forestry and reforestation. I feel there are companies that can help. We have seen some companies that can help clients to do the right investment on the right project. I feel not all the projects will have the same, let's say, monitoring processes to understand if the forest that they planted or that they bought will make sense or not. Obviously, it's something that takes time, so they need to monitor the forest since the very beginning, if it's something that they're planting or they're preserving a piece of forest, because at the end, it very much depends how they deal with the land, that this will be successful or not. But on the other hand, the other options that we have seen around, which are more reliable as well, is the direct air capture. And that's something that is not science fiction. It's happening right now nowadays. There are companies like Climeworks doing this. And what they are doing is capturing carbon from the atmosphere. It's something that happens and you can invest in it. So clients can invest in that. And so obviously, one company like this one can subtract CO2 from the air. Obviously, it's not a silver bullet to climate change, But in the repertoire of offsetting solutions that we have seen around the market, this is a reliable one because it's basically having a direct impact. Every pound that you put into one of these factories, is going to subtract actually some carbon. And it can take to a few of these factories together working in parallel less than a year to offset all embodied carbon of your building. So we don't discard it as a valid option, but we always propose things like that to our clients. Well, as you can see, I think I'm almost done here. So with this, I don't want to really take more of your time. You've seen that it's a lot of information that I throw you here on this presentation. I'm sure you will have lots of questions on how we are doing things and the way we are dealing with that. But overall, what I described here in this presentation is like a path that every architect can really follow to reduce the carbon footprint of their buildings drastically. And it's just a matter of doing the right checks on the right stage and then inform the teams who are doing design with these numbers. Obviously, getting a net zero building is not something that is always possible. We have seen that those who are working in international companies, that how hard it is. But targeting it is what we all should do. As architectural companies, I feel we have some responsibility on that. So at least from ZHA, we are quite conscious about it. And we're targeting this in every single project that we do. And our clients have been responding to this very positively, and directors as well. And hopefully in the future, guys, you will see more results of the new workflows and the projects that we are going to deliver. I think with that, I'm going to leave it here. I'll pass it on to you, Guillermo, and thank you so much for your attention.
Thank you so much for the presentation. It has been great, and the example with the tower, I think, help us a lot to understand all the process and all the workflow and the tools. We have some questions that maybe you can help answering. See, the chat is crazy now. I can't read. But yeah, Alexei was saying that these are mitigating strategies for 80% window to wall. And have these tools help Zaha Hadid Architects designers steer facade designs toward lower windows to wall without compromising design goals?
Yes, I think there are new generations of buildings that hopefully you will see the results. We are trying to work in every single project. I feel like the approach for every project is similar, but there are lots of different factors that what we do normally, we propose strategies, and it's up to basically the client to decide to go ahead with certain things as well. And there are different factors that will probably change the outcome of the amount of glazing. But as a strategy, we're trying to propose this to every single project and try to reduce glazing to things that could be lower than 50%. So obviously, glazing has become the biggest conversation in the industry of architecture, because a lot of people, a lot of engineers are doing amazing products or even amazing studies on how to make energy efficient looking, glass looking buildings. Even if we have a full glass looking building, there are double skin facades behind many of our projects. So you will be surprised to see that very much lots of the buildings that look full glass are very energy efficient because of the layering system that we are delivering there, which still help us to create an energy efficient envelope. But in general, we're trying to reduce it, and our strategy is always constant on asking glass reductions or introduction of double skin facades, basically.
Thank you so much. We have the question from Thomas that I'm not sure if you can answer because it's about the Climeworks system. Is what happens to the carbon when captured with this system with the Climeworks DAC? IAAC?
Yes, Climeworks is very interesting. They are located in Iceland, but they're getting lots of investment from many different countries and people that really want to offset their carbon. So right now, it's a technology that what they do, they just get the carbon inside of a turbine. The turbine has solvents, and what it does through temperature and different physical states inside of that turbine, they dissolve the CO2 inside of that liquid. And in another chamber, what they do, they release it through a rise in temperature. And that thing, what they do, they inject it underground. So you will see that a lot of companies, what they're doing is injecting carbon underground. So especially oil companies, it's surprising to see that they're investing on doing this sort of practice, just to basically on oil wells or locations where they used to have oil, what they're doing is injecting the carbon that they are subtracting with this sort of technology. So Kleinworks is one of them, but I think if you do a little research, you will find other companies doing something similar. And apparently, it's kind of like one of the things that is right now more mainstream because it's really direct, and in a way has a positive impact on reducing CO2. But obviously, I hope that in the future that the technology will scale big enough so it can really contribute to a massive reduction of CO2 worldwide.
Thanks. That's very interesting. Changing from another theme, Mara asked if about the building you showed, the tower, if there are any reflections regarding the results. I'm not sure if it has been built already or it's in...
The project is a research and development project, so we didn't try to basically showcase the workflow, the steps that we need to follow, so people can understand a little bit better, what it takes to make a net zero building or to plan the strategy to achieve a net zero building, either operational net zero and embodied carbon net zero. I mean, the answer for the reflection studies here, because of the shading geometries that we have in the facade, and also the curvature that this facade has, we know it's not going to produce any problem. So our team thought about it in a way that the reflections are not going to affect anything. So it's like the opposite would be to have a concave facades, and that could produce similar to what the walkie-talkie in London did, which we all learned from that. I think thanks to this example, we managed to develop a workflow that can help us to mitigate on early stages any sort of glare issues that our facades could have. But obviously we did our own bespoke approach, so it can work with the Zaha geometries, but it can be easily adapted to any building.
Thanks. And checking the next one is a quite long comment, but it's from Nicholas. He asks about the plugins used for each of the simulation, like solar exposure, wind studies, the light analysis, etc. That you show the debug,
It's on there. I mean, because this is recorded, I think people will be able to see. I think it's the fourth slide. I did a breakdown of the plugins. Mainly is Honeybee, and so Ladybug Tools and Honeybee, and they are connected. They are an interface with Energy Plus and Open Studio. So in a way, the calculations are not happening within Ladybug or Honeybee, but they're connected to that. I mean, certain operations, yes, they happen internally in their components, which are more geometrical, but the calculations of energy happen on a third-party software. I feel like we did our approach on Honeybee and because it's connected to Grasshopper, but other people probably will use IES or any other software for doing their own assessments. But because of the complexity of the geometries that we deal with here in Zaha, for us it was more useful to work directly on a parametric environment like Grasshopper, so we can make improvements or simplifications of the geometry through parametric models. I didn't show that script, but every building has a different script, but probably a person that is skillful in Grasshopper will be able to simplify geometries very, very fast.
Yeah, but you don't have you don't develop in-house plugins, yes, for the simulation.
Well, we have some plugins, but not for the simulation itself.
Yeah. Okay. Thank you. A lot of comments saying thank you. Has been fantastic presentation. Conrad Hoffman says interesting strategy approach. Do you work with auditors, external partners for the nitty-gritty details of energy design?
Yes, a lot. We have different consultants working with us in every single project. Because I mean, the way that our team is structured here, we are like internal consultants, but we don't take liability. So that's our engineers who are basically dealing with the liability in every single project. So we mainly create strategies that later we discuss with them and work with them for validation mainly. But at the same time, what we do helps to the teams to basically forecast before even getting to them how the buildings will operate. So we can simplify it and reduce maybe the time of interaction. This way, they need to invest less resources on consultants. It's quite useful because at the same time, consultants still become, an important part of the workflow. But our team comes first to basically help our designers to take more informed decisions, because we're also integrated on the design process in a way that the consultants are not, especially because the consultants are not that much connected to the geometry process. And our team is highly specialized also on computational design.
Thanks. And another one that looks quite interesting is from Zakaria. He asks if with the 5-step optimization process, are you not finding a locally optimal solution? Why not optimize all of them simultaneously? Like the glazing, setting, massing.
I mean, at the end, it's like imagine this as a checklist. So I feel like there's not like one formula that applies to every place in the same way, especially because if you think about a building, it's not like designing a car. Each building is different. Even in the same location, you can do like 300 different buildings. So we need to really think about a structure to follow, let's say like steps to follow. So when a design comes to us, or like a designer comes to us with a different building, we need to help them understand what they need to do. And so let's say the structure is always the same. That's our, let's say, a recipe. And then with that recipe, we just go through the designers and explain them, the things that we need to include or the steps that we have to follow for validation. And these are always constant. This, let's say, it can be, every climate will have maybe a constant basis in terms of how many steps are we following, or the way we are going to need to deal with the facade geometry. If you work in a cold climate, it's different than you work in a hot climate or in a mild climate. I mean, we know there are buildings that if you do, there are locations, for example, in Mexico or places like similar kind of like climatic zone, that they don't even need air conditioning or HVAC ducts inside the building. They will need like a small air conditioner in one corner that will maybe work for a few days over the year. But for that, you don't need to do a whole HVAC system. So if you are not aware of how the climate is going to help you in one location, the mainstream solution is that let's make a HVAC system with a massive amount of linear meters of ducts, which will have a massive impact on embodied carbon. And at the same time, on the operational side, even if it's not working full time, still embodied carbon would reflect that you have a lot of material there that is sitting there doing nothing. So this sort of studies is what we do, so we can inform internally and understand, what are the requirements for one climate. Then later with engineers, we can fine tune everything and see, what they think about it. And they can tell us, no, you guys are crazy, we shouldn't do that. And we, through this kind of conversations, we either push them or they push us. So it's like a very interesting conversation where we can find ours a middle ground. And thanks to that, we can get a more optimized building. Sometimes we're a little bit more extreme into some topics, but the good thing is that thanks to these conversations in the office, we managed to achieve like very interesting results. So you will see some buildings, hopefully soon, that are quite surprisingly energy efficient, even if from outside they look something else. So looking forward to release this in the future.
Great. Another one asked, with Rhino 8 now out, what features are you most excited for?
We need to work on that, guys. We haven't touched it yet. I know it's coming to us soon, because actually one of my guys told me today, we're going to have Rhino 8 next week. So I'm really looking forward to play with Rhino 8 and see what we can do. I mean, I've been like Rhino as super user since 2008. So I've been working with your tools for a long time, guys. But I'm hoping that Rhino 8 will have like lots of cool stuff that we can play with. That maybe for the next webinar we can do it. Okay,
perfect. Let's see, this not stopping. Greg Tomon asks again about the plugins, and asks if Ladybug and Honeybee are better for you than the Climate Studio or Cove tool. I'm not sure how it's called.
Good. Yeah, I'm aware of these plugins, but we have tried them before. But obviously, we try to use things that you need to pay for. So the thing is that we have been really happy with the versatility and flexibility of Honeybee and also the licensing. We started to work recently with pollination. So I'm hoping in the future we have more tools and more workflows developed with all the pollination ecosystem, because we think that's also very, very nice. But yeah, I think right now the budget was one of the main drivers to stay on those tools, so we can still develop things, customize them, and work in a way by crediting them all the time. As you can see, I'm super happy, and I really like working and talking to Mustafa and Chris Mackey about the things that we're doing. So we always credit them, because at the end, their tools help it a lot. So they help a lot our team to develop custom workflows, and we have been really in touch with them for doing a lot of things that we have done and validate them and be sure that they will work correctly. So they have been incredibly useful, and yeah, if they listen to this, thank you guys.
Thanks. And yeah, another question from Dino. He asked if these strategies have been used not only for new projects, but for to achieve environmentally conscious retrofitting projects. So in projects that have to be rebuilt, or
so can you repeat the question? What's the question?
Yeah, I'm trying to read it. Have these innovative strategies been used for the transformation of existing buildings to achieve environmentally conscious retrofitting projects, not just targeting new buildings?
Yes, that's a good question. I mean, this office has some retrofitting examples, but mainly we're working on new builds. That's why we have focused on new builds mostly, because that's normally the way ZHA operates. We have examples of past retrofitting projects, but they predate us. So to be honest, our team has been in ZHA, like the way it's working right now, for 3 years. But before, we didn't have the chance to work. I was on my own here doing different things on the office, trying to set up, the infrastructure. Basically, took me a year to get it done the way it is right now. And with the team, with the guys that I'm working with right now, it's been more recent. So I feel like all the retrofitting projects predate us, to be honest. So I'm hoping that in the future, if retrofitting projects come our way, we'll have the chance to apply these tools. But definitely, that's something that I would love to, because there's like lots of opportunities on retrofitting. And I feel one of the things that we will need to think in the future is like all the architects and all the companies will need to work on retrofitting in order to, reverse climate change, because most of the embodied carbon, also of the operational energy that is being wasted, is because of the lack of insulation and the poor quality of existing buildings, which, living in London, we're all well aware of that. So yeah, I'm hoping that in the future we have the chance to work on this and tackle more retrofitting projects.
Okay, thank you. And just the last few questions. This one from Thomas. Have you made any data open source on climate studies data around the world, particularly the global locations for buildings?
No, that tool is something that remains still internal. But yeah, in the future, it's something that if we manage to develop in a standalone mode that can be released, probably that's something that could be publicly available. We are kind of writing a paper about it, so hopefully we'll release soon a little bit of the information and the steps that we follow for doing tools like that. But yeah, for the moment, it still is in our, let's say, household.
Okay, I have one other question. I'm not sure if you know what this is, because I don't. Have you ever thought to use pollination to send the geometry model from Rhino Grasshopper to something like IESV? I don't know if it's a plugin, if it's a
Yes, yeah.
Okay.
Yeah, definitely it's something that we start considering if we should add more tools. And I feel like, yeah, we have been doing like double checking and validations through different workflows. But yeah, in the future, we'll love to work with IIS. At the moment, my team is really focused on this sort of tools, but it should be very useful to work with IIS, especially because IIS has a lot of features that we have seen that could be mainly useful for this sort of validation of processes. But at the moment, we are still working with the tools that I showed you earlier. And that's something that probably we'll consider that in the incoming months, because it was a conversation that we have open internally recently about integrating them. But obviously, we'll need to hire more people for running this. And then with the size of the team that we have, it's hard to focus on every single piece of software that is around there for doing this sort of analysis. But yeah, we see that the integration could be quite interesting, especially for our workflow like the one that we developed here.
Okay, thanks. And the last one, because we're running really out of time, from Danny says he was wondering if why is Zaha Hadid not outsourcing the simulations and physics calculations? I think you already answered it with the presentation and this process of informing the decision of the building, but if you
I think I explained some of the reasons earlier. I mean, as internal, what happens like when you do things externally and you outsource this to someone else, first, the time it takes for an engineer to do it is going to be considerable. If you have a team in-house that is basically working at the same speed as your designers, which if you are from an international practice, you know what I'm talking about, things go crazy from time to time. Suddenly, you need to develop 15 iterations or 15 different studies in parallel for one single project. And the engineers probably will give you a time frame, which is quite reasonable, but architects do it very fast if they're inside of the company, working at the same speed or integrated in the teams where they are. So for us, we found a balance in between working hours and speed of analysis. So in a way, we're quite happy, and without even working extremely crazy hours, I'm not saying that sometimes things go sideways, you still manage to deliver very fast results very quickly, which helps the teams to inform their decisions faster. Because if someone tells you, okay, I have these 3 geometries today, can you give me this? Maybe if you can deliver that in 2 days, you're still on time for them to adapt the geometry. But they're not going to stop working because of you doing your analysis. And that's reasonable, because when you're working for competitions, your budget is very small, because normally you're not getting paid for the competitions, not all the time. And so that means that you have less time to work, but still you need to deliver a very energy efficient building. That's what the world is expecting from you. But when you have like 1 or 2 or 3 weeks to deliver a project from the beginning to the end, it's very limited. So if you have to do it on outsource your results, it will take longer. And at the same time, it's like a back and forth process that can take more time, because you don't know when they're going to reply to you. But if you have one guy sitting next to you, or next to the engineer, or next to the architect, the interaction is very fast. It's like, hey, Carlos, can you help me with that thing? And then, yes, I can. So when do you need it? For this afternoon. That's not going to happen, but maybe you give me 2 days, we can have it for you. And that's normally the type of conversation I have with our architects and our directors here. So they understand the time it takes. I think they understand it more now. At the beginning, it was more challenging, but it's been very fun and very nice, because at the end we managed to create a very nice working environment for us and for them, and they know that we were fast. So I think like if you do the same in other architectural practice, at certain point, everybody balances their rhythm based on the needs of the other, and you find a way to deliver things. So for us, it's very important that you do that thing in-house, you deliver way earlier results, and then you can adapt your design faster. If you do it in later stages, it's very hard to change your design, because things go very fast. At a certain point, when the results arrive, nobody changes anything. And that's what we realized, that doing this in-house was more efficient. And that helped us to deliver better projects when you go to competitions, especially.
Well, thank you so much. That has been all. I think there are a few questions, but I have no more time. But it has been great to see the presentation and the workflow. And thank you so much for being our guest today.
Thank you, Guillermo, and thanks to the sustainability team and to my guys who have done this presentation possible. I've been working a lot with me to put everything together. And we've been doing even like simulations and stuff for the last week and a half to really show you a very nice and compelling structure of steps. I'm hoping that people find it interesting. So yeah, if someone has any questions, they know where to find me. Thank you, Guillermo. Thank you, Manuel, for the opportunity of being here. It's been a pleasure.
Thank you so much. Have a nice afternoon. Bye.
Take care. Goodbye.
You too.